Swayam Prabha. Digital India. Educated India.
We have already finished 3 modules, starting with the basics of probability, then the second model is random variable, and the third model is moments and inequalities. Now we are moving into the fourth model, that is called standard distributions. In this model we are going to discuss various standard distributions, which includes standard discrete random variables distributions and distributions of standard continuous type random variables. Standard means whenever we solve the real world problems, some distributions comes very often. So those distributions we call it as a common distribution or standard distributions, or frequently we come across the same distribution again and again. So those distribution has some name, therefore we call those distribution as a standard distributions or some common distributions. So first let me discuss a few standard common discrete type random variables whose distributions and also the moments, in particular mean and variance. And similarly we will discuss later some common continuous type random variables and their distributions, also the mean and variance for those distributions. Then we will discuss some of the problems which has the underlying distributions. So in this model we are going to make 3 lectures that is the title of the model is standard distributions. In this, first we are going to discuss some common discrete distributions. Second, we are going to discuss some common continuous distributions. Third, we are going to discuss some applications of random variable. That means we are going to discuss some problems which are related to these common discrete and continuous distributions. Let us start with some common discrete distributions. The first one which we are going to discuss, that is called a constant random variable. A random variable x is said to be it is a discrete type random variable. X is a discrete type random variable is said to be a constant random variable whenever the probability mass function of that random variable x takes one single value A with probability 1. A can be any in the real. That means the whole unit mass is accumulated at the point x is equal to A. That means in a random experiment you may have a sample space with finite elements or countably infinite or uncountably many elements. The way the real valued function is mapped from omega to r, it is a many to one function. Therefore, the probability of x is equal to A is nothing but the collection of all possible outcomes which gives the value A, that is this is omega, it has so many elements. So, the mapping from omega to r at the point A for all the points. For all possible outcomes, the mapping is A, where A is belonging to real line. That means the probability of x equal to A is nothing but it is a probability of P of omega. From the Kolmogorov axiomatic definition, we know that the P of omega is 1. Therefore, it is going to be a probability of x equal to A is equal to 1. That means all other points, if you go for the inverse image, whose mass is going to be 0. You can draw the CDF of this random variable. Suppose A takes some negative value, then the f of the CDF is going to be 0 till A. At the point A, it becomes 1 and it will be 1 till infinity. That means the CDF has only one jump and the jump value is 1. It satisfies all the properties of the CDF. Therefore, you can conclude this is the CDF of the random variable. And if you draw the probability mass function for this discrete type random variable, at x is equal to A, it has the value 1 and all other point the mass is 0. That means the whole unit mass is accumulated at only one point. Therefore, it is called a constant random variable. That means any constant can be represented as a random variable with the probability 1 at that point. It is a very important result. The CDF has only one jump and the probability mass function is at only one point with the value 1, otherwise it is 0. Therefore, the probability P of x can be written in a easy way. It is equal to 1 when x is equal to A, it is equal to 0 when x is not equal to A. So, this is the probability mass function and this is a CDF, and this diagram gives the probability mass function in a graphical form. Now, we will go to the second one, that is called a Bernoulli distribution. A discrete type random variable is said to be a Bernoulli distributed random variable when the probability mass function takes a value 0 is 1 minus p and the probability of x takes a value 1, that is p, where p is lies between 0 to 1. Otherwise, it is 0. That means, the probability mass function p of x, it takes a value p of x is p when x takes a value 1 and 1 minus p when x takes a value 0, otherwise it is 0. You can draw the CDF this discrete type random variable. X takes a value 0, so till 0 it is 0. At 0 there is a jump, of height 1 minus p. At the point 1 it has another jump, that jump value is p, therefore, it touches 1. That means, for this discrete type random variable, the CDF has 2 jumps. One jump is at 0 with the jump value 1 minus p, and the next jump at the point 1 with the jump value p. Therefore, this is a discrete type random variable, and you can draw the probability mass function also in the similar way. So, at x is equal to 0, the height is 1 minus p, height 1 minus p. At x is equal to 1, it has a jump p. It depends on p is going to be less than 1 by 2 or greater than 1 by 2. Accordingly, you will have a 1 minus p with the shorter height and the p is taller comparing to the mass at the point 0. Whenever the random experiment has 2 possibilities, we call it as a Bernoulli trial. Suppose you treat one possibility as a success and the other possibility as a failure, then we usually denote the success probability with the probability p and the failure probability with the 1 minus p. Then that type of trial is called a Bernoulli trials. A discrete type random variable with the probability mass function of this form, we call it as that random variable is Bernoulli distributed. Always the p has to be open interval 0 to 1. If p is equal to 0 or 1, then it becomes a constant. Therefore, it has to be always the open interval 0 to 1, which gives a Bernoulli distributed random variable x. Now, we will go to the third one, that is a binomial distribution. When we say the given random variable is a binomial distributed, this also discrete type. Whenever a discrete type random variable whose probability mass function is of the form p of x, that is equal to n c x p power x 1 minus p power n minus x, when x takes a value 0, 1, 2 and so on till n, otherwise it is 0, then we call or we say the random variable, which is a discrete type random variable, has binomial distributed random variable. Since this is a probability mass function, this is always greater than or equal to 0, and if you make a summation over x from 0 to n, that is going to be 1, and here the p value is always lies between 0 to 1, and n is the positive integer. The probability mass function of the form n c x p power x 1 minus p power n minus x. Once you know the value of p and n, you know the probability distribution of this random variable. Therefore, we call n and p are the parameters of the binomial distribution. So, we usually write the notation x follows, this tilde means follows, capital B, that means for the binomial distribution, and here the parameters are n and p, therefore, n comma p. So, whenever we write x tilde capital B within bracket n comma p, that means the random variable x follows binomial distribution with the parameters n and p. If you supply the value of n, which is a positive integer, and small p, which lies between open interval 0 to 1, then you are known with the probability distribution of this random variable. The probability mass function has this form. So, you can make out the CDF of binomial distribution has n plus 1 jump points and the corresponding jump values are ncx p power x 1 minus p power n minus x. So, this is a discrete type random variable. So, you can see the CDF at x is equal to 0, it is a first jump, at x is equal to 1, it has the second jump, at x is equal to 2, it has another jump, and so on. At x is equal to n, it has the last jump, and which gives the value 1. So, this CDF is a right continuous function with n plus 1 jump points, and the jump values are the ncx p power x 1 minus p power n minus x. As a special case, when n is equal to 1, then the same random variable is going to be, say it as a binomial distribution with the parameter 1 comma p, that is nothing but a Bernoulli distribution. When n is equal to 1, you will end up a binomial distribution. So, the probability mass function is going to be at x is equal to 0, it is 1 minus p, at x is equal to 1, the probability mass is a p, therefore, it is a Bernoulli distributed random variable. One can create a binomial distribution with the help of a Bernoulli distribution, that is whenever you have a random variable. Second remark, we can treat this as the first remark. The second remark, whenever you have a Bernoulli distributed random variable with the parameter p for n such random variables, if you create one random variable as a sum of xi's, I is equal to 1 to n, that means each random variable is a Bernoulli, that means either it takes a value 0 or 1, and if you create a random variable of sum of n such Bernoulli distributed random variable, and you can make the one assumption all are independent random variables. In detailed, what is the meaning of those n random variables are independent and what are all the properties going to be satisfied, that will be discussed later. But now you can keep the assumption xi's are independent random variable, that means it is they are mutually independent random variable. Then one can conclude the capital X is a summation of xi's. So, now the possible values of x is going to be 0 to n, because each xi's takes a value 0 or 1. Therefore, sum of n such Bernoulli distributed random variable, the possible values are going to be x, and you can get the probability mass function. It is x takes a value small x, that is going to be ncx p power x 1 minus p power n minus x, when x takes a value 0 or 1 or 2, so on till n. That means suppose you say that x takes a value small x, that means out of n such Bernoulli trials you are getting x with the probability p, and the remaining n minus x you got the failure, that is 1 minus p power n minus x with the possibilities of nc ways. Therefore, the probability of x equal to small x is going to be ncx p power x 1 minus p power n minus x. So, this is going to be a probability mass function of binomial distribution. Therefore, one can conclude if you have a n independent Bernoulli distributed random variables with the same parameter p for the Bernoulli distribution, then the sum of n independent Bernoulli distributed random variable becomes binomial distribution with the parameters n and p. So, we can say x follows a binomial distribution with the parameters n comma p. So, this is a way one can create the binomial distribution with the help of a Bernoulli distribution. As a third remark, we can go for finding what is the MGF of binomial distribution. Suppose x follows a binomial distribution with the parameters n and p, you can find MGF of binomial distribution, that is nothing but expectation of e power x times t, that is same as, since it is a discrete type random variable, so it is going to be summation e power x small x t, and the probability of x takes a value small x, and the possible values of x are from 0 to n. So, you substitute all the values, that is x equal to 0 to n e power x times t, and the probability of x equal to small x is n c x p power x 1 minus p power n minus x. Now, also you do not need to expand and simplify and so on. You can keep p power x and e power x t together. Therefore, this is nothing but summation x is equal to 0 to n c x e power t times p whole power x and 1 minus p power n minus x. Therefore, the MGF of binomial distribution is p e power t plus 1 minus p the whole power n. Using a binomial summation, you can get MGF of binomial distribution is p times e power t plus 1 minus p power n. What is the use of MGF? Once you know the MGF, you can get all the moments by successive derivative. If you want to find out only mean, you can use the mean definition and you can get the mean. Suppose you need many moments, then better you can find the MGF first, then successive derivative, and I have already explained from the moment generating function how to get the moments of order n. So, you can use that and find out the first order moment, second order moment, any nth order moment. So, in particular, if you want to find out the mean of this random variable, if you want to find out the mean of this random variable, that is nothing but if you use the derivative one, derivative of MGF with respect to t, then substitute t equal to 0 will give the mean of the binomial distributed random variable. So, by doing the derivative and so on, you can get the value n into p. This is a one way of finding mean of the binomial distribution, or you can find out from the scratch, that is a summation, that is a summation of x times probability of x equal to x, where x takes the value 0 to n. So, that is same as summation x equal to 0 to n x times n c x p power x 1 minus p power n minus x. You can cancel x with n c x one term, therefore, you will get factorial n divided by n minus x factorial and x minus 1 factorial. So, now you can keep 1 n and 1 p outside. Therefore, the simplified quantity becomes n minus 1 c x minus 1 p power x minus 1 and 1 minus p power n minus x. So, that is nothing but p plus 1 minus p power n minus 1, and you know that that value is 1, therefore, this is going to be n into p. So, there are two ways you can find out the expectation, either from the scratch by the definition method or by the MGF method. The same way one can compute the variance. So, the variance of x, that is going to be either by using the definition. For that you have to find out the expectation of x square, and already you know the value of expectation of x, you can substitute, you can get the value, or you can do the second derivative of the MGF, then through that you can get the variance. So, if you do the little simplification, you can get the variance of x is going to be n into p into 1 minus p. For that you can do the other method, that is you can find expectation of x square, that is nothing but second derivative of MGF of x with respect to t twice, then substitute t equal to 0. That simplification will give the value, that is n into n minus 1 p square plus np. So, once you know the expectation of x square and substitute in the variance formula, that is n into n minus 1 p square plus n into p minus n p the whole square. So, you simplify that, you will get the value, that is n into p into 1 minus p. So, this is the way one can get the variance of x for the binomial distributed random variable. There is another observation. If you draw the probability mass function of a binomial distribution, for n is equal to x is equal to 0, you will have some height. For x is equal to 1, you will have another height. For x is equal to 2, you will have a more height, and so on. Then it will be keep decreasing. So, this is based on the value of p, you will have a increasing for the different values of x, then decrease. For p is equal to less than half, you will have a more increase in the first half, then it goes decrease. For p is greater than 1 by 2, you will have a less heights in the beginning and more heights in the second half. If p is equal to 1 by 2, then you will have a very symmetric of increasing and decreasing over 0 to n. And for n is equal to even, you will have 2 heights. For n is equal to odd, you will have only one height. That is the way the values are going to be keep increasing, then it will decrease. I have just drawn one diagram for probability mass function for some n and some p. The importance of the CDF graph is from the finite number of data, and if you draw the cumulative distribution graph, if that graph is same as the CDF of binomial distribution, then one can conclude the data follows binomial distribution. Not only from the CDF, one can do the observation from the probability mass function also. That means if you draw the histogram of the values of the data over 0 to n, and the probability, the histogram look like the probability mass function at some points, if it is almost same, then you can conclude that the data also follows binomial distribution. Therefore, one should always know the CDF and the probability mass function for a discrete type random variable. Similarly, for a continuous type random variable, one should know the CDF as well as the probability density function of a continuous type random variable. So, both the things are very useful when you have a data in the first, then you can identify what could be the distribution.